Today, we are going to simulate a higher order process in deadbeat and Darlin's controller. For that, we are going to use the approximate mathematical model of higher order process. This is very, very important because for any higher order process, it's not possible to get the exact model. Already I told you one example that you want to know the temperature of your water bath. You cannot know the temperature by looking at it. You need an instrument to measure the temperature. You are looking at the temperature not at the bath. You are looking at the temperature at the thermometer. So thermometer is now cascaded with the water bath. That's why now the system becomes second order. If thermometer has first order of 5 seconds time constant and the process has a time constant of another 5 seconds, now the system becomes two first order cascaded. So then it is overdamped. So like that, you are getting second order. In the same way, if you look at the process in our lab, it has many components in cascaded. If we take the forward path, it consists of controller. Controller output is connected to, if it is a digital controller, it consists of a DAC in the output. The DAC output is connected to zero order hold. Zero order hold is connected to the I2P if it is a valve. I2P, then I2P is connected to access, connected to I2P is connected to final control element, say valve. Or the controller DAC output is directly connected to VFD as a final control element. So in the forward path, 4 or 5 components are there. Therefore, numerator itself has fourth order or fifth order. In the loop, if you see in the feedback path, it consists of a sensor in addition to these forward path. That's why any higher order process having unknown parameters. We do not know the parameters of sensors, control valve, final control element, I2P, PID controller. Those mathematical models we do not know. But level we can obtain. Suppose we are controlling level means from the first principle we can obtain the level model of the mathematical model of the level. But of course it will be a first order. But it is not so in practice. That's why we would obtain approximate mathematical model from the reaction curve. That reaction curve will give only approximate model. So now we can understand that the purpose of mathematical model. Mathematical model is used to design the controller. Now let us obtain one such approximate model for that fourth order process, 1 by s plus 1 to the power 4 that we are going to control. For that, let us find the approximate mathematical for that. Then we will design the controller by using that approximate model. Today, we are going to see the design of Darlin's controller. The controller is this: 1 by HGP of Z, 1 minus e power minus t by mu z power minus k minus 1, 1 minus e power t by mu z power minus 1 minus 1 minus e power minus t by mu z power minus k minus 1. This is yesterday we have seen how we obtained that. Here t is the sampling period. T is the sampling period. We are going to consider the system 1 by s plus 1 to the power 4 that we are going to consider. We are going to control this. So sampling period we are going to assume as 1. Now first let us obtain the mathematical model. To obtain the mathematical model, we have to get the reaction curve. We have to get the reaction curve like this. For that, what you have to do? You have to take the process. You have to take the process 1 by s plus 1 to the power 4. Then give a step change. Then you will get the reaction curve. You will get the reaction curve that you got here. So in that, if you see the dead time, it is 0.68 seconds. Therefore, dead time equal to TD equal to 0.7. Then if you see the time taken to reach 63.2%, that is the time is 3.259, 3.259 seconds minus the dead time approximately 0.7. If you subtract, you got 2.559, say 2.6 seconds. So the time constant is 2.6 seconds. Therefore, the approximate mathematical model of the process is e power minus 0.7 s upon 2.6 s plus 1. Here kp equal to gain equal to, you gave unit step input, you got unit step change. That's why 1 by 1 equal to 1. So what is the mathematical model? Approximate first order plus dead time model, kp e power minus tds upon tp time constant times s plus 1. So if you substitute the time constant 2.6 and dead time 0.7, you got this model. You got this model. Now we have to find now we have to find the now we have to find the HGP of Z. HGP of Z. Why? Because GP of S is a continuous time system. That's why we cannot give discrete input to that. That's why we have to include HGP of Z. So 1 minus e power minus ts upon s multiplied by, now you have to consider the model, not the process. You do not know the mathematical model of the process. Here in simulation only we know 1 by s plus 1 to the power 4. That's why we have to consider this model to design the controller. That is e power minus 0.7 s. So if you obtain Z transform for this, you will get 1 minus Z power minus 1. Remaining part Z transform of e power 0.7 s upon s multiplied by 2.6 s plus 1. So if you take this also approximated to 1, because we assume that sampling period equal to 1. The 0.7 is approximated to 1 sampling period, 1 second. Then that also came out as Z power minus 1, because 0.7 is approximated to 1 second. So 1 minus Z power minus 1 for this. So now for this you are getting 1 minus Z power minus 1. For this dead time you are getting Z power minus 1. Then for remaining thing, you know that SA divided by A upon S multiplied by S plus A. If you use that, for that, if you find Z transform for this, you will get 1 minus e power minus AT Z power minus 1 upon 1 minus Z power minus 1, 1 minus e power minus AT Z power minus 1. So if you substitute this also, you can take out what you will get. You will get A equal to 1 by 2.6 you will get, and here A equal to 1 by 2.6. That's why here we substituted T equal to 1 by 2.6, 1 by 2.6, A equal to 1 by 2.6. So you got this. If you this is the mathematical model. This is the mathematical Z transform of HGP of Z. I am not putting GP, I am putting GM, process model, PM or M, or simply put M. I am putting M because I am not putting P. If you put P, you cannot distinguish between the actual process and this. So we are taking the approximate model and we got HGP of Z. Now we can design deadbeat controller. To design deadbeat controller, you consider this. What is deadbeat controller? Deadbeat controller is 1 by HGP of Z multiplied by Y of Z by Y set point of Z, Y set point of Z whole divided by 1 minus Y of Z upon Y set point of Z. Y set point of Z. So if you substitute, what is HGP of Z? 0.32 Z power minus 2 upon 1 minus. If you have to write inverse of that, and here T equal to 1, t equal to 1. Dead time also equal to td also equal to 1 second, we assumed. So 2 seconds minus k minus 1. So here y of z by y set point of z equal to z power minus k minus 1. K equal to 1, therefore z power minus 2. If you substitute that, you will get z power minus 2 upon 1 minus z power minus 2. If you simplify, you will get this. If you simplify the above expression, you will get this. Now we have to check whether the controller is physically realizable or not. To check whether it is physically realizable or not, first step is all must be in negative powers of z. First write all in negative powers of z. Then that is written. Already it is in negative powers of z. So it is in negative powers of z. Then at least one term must be without z. Constant term must be there in the denominator. All must be in negative powers. All must be in negative powers. Then first step. Second step is your denominator must have a constant term. Otherwise, you multiply numerator denominator by some z. You will get one constant term. Suppose here you are having z power minus 1 instead of 0.32. You are having, suppose I am having the denominator 0.32 z power minus 1 minus 0.32 z power minus 3 I am having. So suppose I got like this. What I have to do? Multiply the numerator denominator by z. You will get 0.32 minus 0.32 z power minus 2. So like that you will get one constant term. Once you get, you have to check whether any positive powers of z in the numerator. No positive powers. That's why physically realizable. So that is the first step. We have to check whether the given the designed controller is physically realizable or not. Yes, it is physically realizable. Next step is you have to check whether the system, any poles is outside unit circle, whether the controller is stable or not. You have to check whether the controller is stable or not. Here, what is the denominator poles? 0.32 z square. After, then one more step. After obtaining this, you say that it is physically realizable. After that, convert this into positive powers. What is the highest, lowest, we can say like that, lowest degree of denominator, z power minus 2. So multiply the denominator and numerator by z power 2. That's the lowest. Change the sign. Here z power minus 2 is the lowest. Change the sign. 2 plus. Multiply the numerator and denominator by that. So you will get this. So now it should be in this form. Then only it will, you can enter. It should be in positive powers of z. You should not enter negative powers of z. Otherwise, you will get wrong result. That's why you will, you should enter like this. So if it becomes positive powers, you know, then you have to check the poles of that. If you check the poles, what is the denominator polynomial? 0.32 z square minus 0.32 equal to 0. So z square equal to 1. Therefore, z equal to plus or minus 1. So it is on the unit circle. Therefore, the controller is stable controller. It is almost equal to, in S domain, it is on the j omega axis. If you include a 1 by s term integrator, if you include that, it works in closed loop. It becomes first order like that. Even though it is also an integrator, it indicates that it is also an integrator, but it is on the unit circle stable. If it is outside unit circle, unstable. Exactly on the unit circle, therefore stable. Now we have to enter these things in simulation model. So how to enter those things? First thing is you have to take a step function, because we are going to check the system for step response. So set point will be a step function. So you have to take a step function. Then discrete transfer function you have to take. Why? To enter the controller in positive force. You have to enter like this. Here z square is there. So what you have to enter in that bracket, coefficient of z square is 1. Then what is coefficient of z? minus 0.68. Then what is coefficient of z power 0? That is constant term. Nothing is there. You have to put 0. So like that, you have to enter in the numerator. Denominator, how you have to enter? Denominator in that block, you have to enter z square 0.32. You have to enter. Then no z term, so 0. Constant term minus 0.32. You have to enter like this. So you got controller is over. Zero order hold with sampling period equal to 1. You have to take. Then we have to enter the process. How to enter process? To enter process, you have to consider this. Here, the process is 1 by s plus 1 to the power 4. Expand this. What you will get? 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6. If you add these two, 6, 4, 1. So what you will get? S power 4 plus 4 s cube plus 6s square plus 4s plus 1. So this you have to enter in the denominator. That's all. So you enter this here in the transfer function. This is continuous transfer function. Then put a scope from the sync module. You can get scope. Then take a summing junction. Then connect all these things as shown in figure. Then you will get the deadbeat controller. This is the deadbeat controller. Now let us simulate the deadbeat controller. You should drag this sync function where it is available. It's available in sources. If you get into that source, yes, step function is available. Yes, where is that step function? Yes, it's available. You can drag and drop. You can drag and drop. By doing that, you can get this. Like that, you have to get all blocks. All blocks you have to get. Then similarly, you have to get this discrete transfer function. This is a discrete transfer function. Or you can enter in the search. You can enter discrete transfer function. You will get that. Then zero order hold. You have to drag and drop. Again, you have to drag and drop the transfer function. Continuous time model. This is continuous time model. This will be in bracket yes. You see that here this is bracket in z. Here yes. So that's all. Then you have to get this scope from the sync scope, or you can search and get scope. All you got, then you have to connect them like this. Here you have to check whether the sign is negative, because if you take any block, automatically it will be positive. So you have to change the sign, double click and change the sign. Plus minus is changed. Everything is ready. Now here, what you have to enter? Step time is 0. Here it will be 1. Default will be 1 step time. That you have to change. Then final value will be 1. Initial value will be 0. Step time is 0. This alone you have to change. Here you have to enter 0. Then here you have to change that plus minus, because negative feedback. This is summation block. This is a summation block. It is available in maths, or you can search and get summation block. Then here in the discrete transfer function, we have to enter the controller. What we got? The controller we got is numerator. Already I sent the papers to you. Is that square? That's why -1 we entered. Already we have seen that this is physically realizable. And we checked whether the controller is stable. That also we checked. Then coefficient of z you enter. No constant term, that's why you have to enter 0. So it must be in positive powers. Then we have to enter denominator. Here coefficient of z square is 0.32. Then no z term, that's why 0. A constant term is there, that's why minus 0.32. So we entered all these things. Zero order hold, you have to check the sample time is 1. If t equal to 1 you selected, you have to put t equal to 1. Then you have to enter the transfer function 1 by s plus 1 to the power 4. You expanded, that is coefficients are 1, 4, 6, 4, 1. That entered in the denominator. That's all. We entered. Now we can get the servo response. Now we can get the servo response. Yes, now we can get the servo response. Yes, this has a large overshoot. Suppose I am replacing this by the same model. What is that model we obtained? Model is 2.6 and 1. That's all. That is first order. Then you need a transportation lag. And then you need a transportation lag. Yes, I got the delay. Variable transport delay I got. So what is the model? Model is we assumed as time delay of 1. Yes, even though it is 0.7, we assumed it as 1. So now model and system are identical. Model and system are identical. Now if you run what you are getting, you see, you got the exact no overshoot. But in the book it is written that all, you see, are you able to see? Are you seeing? Trinity?
Yes, sir.
Okay. Step response. There is no overshoot. But in the book, it is written that if it is deadbeat controller, there will be overshoot. There is no overshoot at all. What is our assumption? After one sampling period, let us simulate for 10 seconds or 5 seconds. After one sampling period, it is coming like this, no overshoot, but it takes 2 sampling period to come to 1, but no overshoot. But in the book it is written that it has a large overshoot and then settle. If process and the model are identical, then there won't be any overshoot in that process. Now I think you got. If you simulate for 100 seconds, you can't see this delay also. It takes 2 sampling period to settle at 1. If you give 100, it appears like this. So it appears like as if it is settled at 1 sampling period. But if you amplify, you can notice that it settles at a third sampling period. But anyhow, no overshoot at all. That's why if there is a mismatch between process and model, then only there will be a overshoot. That point is not mentioned in the book. That is for your information. Now let us introduce some disturbance here. For that I am putting one more this block here. Yes. We'll give here what is there. What will be the direction? Now we are going to give disturbance, step disturbance, and how it behaves. We are going to see here. There is no mismatch between process and model. We are going to give positive disturbance, so we have to put the plus sign. Positive. Negative disturbance means let it be minus sign. There is no step change. That's why we have to give final value also 0. That we gave. Here, step time is final value is 1. We are going to give step input. Now let us simulate what happens to the system. If you see that, It is also, you simulate for here there is no oscillation. There is no oscillation. There is no a step input of 1 unit is given, so it goes to 1. The next sampling instant it comes to 0 because the process and the mathematical model are identical. If you simulate for 10 seconds, you can amplify and see the 5 seconds. Let us take for 5 seconds. You can amplify much and you can see the response. You see, there is no overshoot at all. Because of disturbance is unity. That's why it goes to 1. Then again it comes to 0 in the 4th sampling instant. That's all. No overshoot and all. No oscillation and all. Because the mathematical model is perfect of the process. That's why no oscillation. On the other hand, if you see, if it is a 4th order process, negative, how it behaves. How to change this negative? You can give final value as -1 here, or you can change the sign there. Final value is -1. Here also you can change. -1 also you can give. Negative step change. So I am changing this way. So I'm what you are getting. Yes, it comes down by -1, then it goes up. In 4th sampling instant, no oscillation, no overshoot, no oscillations. No overshoot at all because disturbance is 1. That's why it came to 1. It is not overshoot. No overshoot at all. So this is because the process and the model are identical. The process and model are identical. But on the other hand, if you take the process, 4th order process, 1, 4, 6, 4, 1. Now, the process and model are not identical. And we are going to do for disturbance, negative disturbance. Simulation is for 5 seconds, 100 seconds. Oh, what happens? Y-axis, see the y-axis? It came to -1 because we gave negative step change, and it has oscillations, large overshoot. You can notice that large overshoot and oscillations, and then settles. This is practice. This is practice because we cannot get the exact mathematical model of process. We will get approximate model only. That's why there will be a large overshoot. If you design Darlins for this, there won't be this much overshoot because we are specifying the responses like first order with dead time. That's why there won't be any this much overshoot. Now let us do the same thing for positive disturbance. For that, what you have to do? You have to change this. Let us give the disturbance after some time. Then you can see the response. So you will see after some time. Now you see, you can understand what is disturbance. It appears like a servo response. That's why you may get confusion. Now you can see disturbance is given where initial value is 0, then final value is -1. Okay. Step time is 1. Now you check. Yes, servo response. Here also large overshoot, large number of oscillations that you can see. So how to design a deadbeat controller for a higher order process? You have to obtain the reaction tau. I took 1 order less, 1, 4, 6, 4. So what? Now, what you have to do, you have to give and scope. Give simulation. You simulate and take this. This is the reaction curve. Yes, this is the reaction curve. So if you select this measurement, you can take the dead time is draw a line, tangent is it cuts here. So it's 1.2. 1.2. So actually 1.2. Let us 1.2 seconds. Dead time is 1.2 seconds. What is time constant? You select 6.23. What is that value? 6.6. 6.23. Here I have to move this. 6.2. 6.32. Sorry, 6.32. What is time now? You see here 4.356. Subtract 1.2 from this, you will get 4.1. Sorry, 3.1, 3.2. I think most of you got 3.2. I think so. So 1.2 seconds as dead time and 3.2 seconds as time constant. So I didn't draw